All right, as we get started today, I want to begin by quickly reviewing what we were talking about yesterday. We were focusing our time and attention primarily on right triangles, and we said that for any right triangle, the three sides are related according to a particular equation. Ethan, what is that equation?
Pythagorean theorem.
The Pythagorean theorem, right? Which is what?
C squared equals a squared plus b squared.
Good. So for any triangle, doesn't matter, or any right triangle, excuse me, doesn't matter if it's got particular angles or whatnot. We know the square of the hypotenuse is going to equal the sum of the squares of the two legs. But we have a couple of other right triangles that we talked about last year, we reviewed over yesterday, some special triangles that have a 30-degree angle, 60-degree angle, and of course the 90-degree angle. And in a 30, 60, 90 triangle, we don't need to know two sides in order to find a third side. We can know just one side and find the other two, because the sides are related a particular way. First of all, which side in the 30, 60, 90 is x? Quentin?
Shorter leg.
The shorter leg, which of course is going to be across from the 30-degree angle. So in case your judgment of which one's short isn't real good, which should be pretty obvious, it's the one across from the 30. Now here's the kicker. Which of these two sides is the 2x, Jamie?
The 2x is the hypotenuse?
The hypotenuse is the 2x. And then the long leg back to Quentin is x times the square root of 3. So we want to make sure we've got that memorized. Then for this other right triangle, we call it the isosceles right triangle. Both of these angles are exactly how large, Ethan? 45 degrees. So sometimes called a 45, 90, also called the isosceles right triangle. And of course, if equal angles, equal sides, so each leg could be labeled, Jamie, as x. And then the hypotenuse we need to memorize, Chris, is represented
2x.
That would be in the 30, 60, 90. Quentin? X times the square root of 2. So again, most right triangles just use the Pythagorean theorem, c squared equals a squared plus b squared. Or of course the hypotenuse is the c and the a and b are the two legs. Doesn't really matter which one's which. But you got your special triangles here as well. So let's suppose, paper out, calculators at the ready. Let's suppose we had a triangle that had a 14-foot long hypotenuse and a 10-foot long leg. Find the missing leg. So we've got two more triangles for you to solve as well. Clinton's done. Chris is done. Remember the Goldilocks and the Three Bears? She comes in, Papa Bear goes, somebody's been eating my porridge. Somebody's been using my calculator and messed it all up. There's sticky stuff all over the face of it. I would certainly not need sticky stuff on my calculator. That's sacrilegious. If this were Casio, it wouldn't matter. But this is a Texas Instrument TI-30XA. You don't get stuff on.
Are those expensive or something?
No, it's just the best calculator ever made. You don't get messy on Best calculator ever made.
Most calculator ever made is the one that's on your phone.
No, piece of junk.
Oh. Just like your kids.
All right.
Got that back.
All right, so let's take a look at these here. We got the first triangle, hypotenuse 14 feet, leg 10 feet, finding the other leg. Is this a special triangle, class? No, just a big nothing. So we're going to square the hypotenuse, and then we're going to have to subtract over the square of the leg, which of course is 100. And so when we subtract it, that's going to give us the square of this leg. But if you got 96, shouldn't that seem a little large? 96? That seems massive. The nice thing is in this class, when you get an answer like that, you're like, that just doesn't seem right. You forgot to take the square root. And we take the square root of it, we'll get a rounded off answer of 2 sig figs, 1 sig fig. But I said in this class, we're going to use at least 2. So we're going to round it off to get anyone? 9.8 feet. Almost an isosceles right triangle, right? Almost equal legs, not quite, and not quite equal. How many got the 9.8 feet for the first one? On the next one, we were given a side, a hypotenuse of 4 yards. We weren't given either leg, but it didn't matter because we knew there was a 30-degree angle, which means we have, Chris, a
30, 60, 90.
Remember with the 30, 60, 90, I would start by labeling everything. We would label this hypotenuse as
2x.
2x. So if 2x is 4 yards, then plain old x class has to be 2 yards. Where's the plain old x?
Across from the 30.
Across from the 30. So there's my 2 yards. And then down here, this is my x times the square root of 3. So if x is 2, then this side is going to be 2 times the square root of 3 yards. And since we were doing exact values, no problem there. If you wanted to, 2 times the square root of 3, 3.46 whatever, 3.5 yards, but I'll just leave it as the exact value. How many got those 2 answers for the second?
I put 3 because I saw 1 sig fig, so it ended up, but it wants to be at least 2, so it should have been
3.5, yeah. Typically with special triangles, we'll go exact values just because that's easier, and I don't want to have to pull the calculator out at all, but you could. And look at the last one. We're given 2 sides of the right triangle. Both legs are 6 yards. Wait a second. Both legs are 6 yards? Oh, it means it's a 45, 45, 90. So without doing any math at all, I already know this is going to be 6 times the square root of 2 yards. Okay? Or you could use Pythagorean theorem and get the same answer. Questions on this? Questions on this? Yeah, 8.4-ish, rounded off to 1 sig fig 8, but I believe rounded to 2 sig figs, either 8.4, 8.5. Questions on this? Now, yesterday I mentioned to you that for a specific acute angle in a right triangle, there is a specific ratio that sides make to each other, because if one specific acute angle is specified, all right triangles with that acute angle would have to be similar to each other, which means all the sides are proportional, which means all the sides form the same ratios, respectively. We have names for these 3 ratios. A name for the first ratio is the sine. You can put this in your notes under trig, because I'm too lazy to write trigonometric. Trig ratios. Trig ratios. First trig ratio is called the sine. Why is it called that? I don't know, but it's called the sine. The second ratio is called the cosine. And the third ratio is called the tangent. Now you might be thinking, wait, tangent, isn't that a line that touches a circle at one and only one point? It is, and you're actually going to see how that applies to trigonometry later. For now, think of it as a separate term that happens to have the same name. Okay? I've known other people named Ethan besides this guy. They're nothing alike. The other Ethan was short. The other Ethan was fairly handsome, but I'm just kidding.
Actually smart.
Anyway, but sine, cosine, and tangent. Now, the key to remembering these trigonometric ratios is to remember an old Indian, Native American saying that means trigonometry is easy because the Native Americans were really smart. They knew trigonometry, right? Look at their TPs. Look at the cross-section. Triangle. They knew their triangles. So they had an old saying, Sokatoa. Sokatoa. Okay? I had a Korean guy in my class one year. It was a old Korean saying, Sokatoa. Anyway, I'm not politically correct, and that's okay. You do need to remember the spelling of Sokatoa. So-ka-toa. Say it with me, class. SOHCAHTOA. Again, you gotta say it with the accent, or it just SOHCAHTOA.
Is this gonna
Does
work
that sound
in
like
the
Georgia?
future?
No, because nobody knows who you are. All right, so
remembering?
SOHCAHTOA. It is recording, but they don't know his name. Right, again, SOHCAHTOA.
So,
Now, here's what this stands for. In any right triangle, if we're going to focus on one specific angle, because again, that's the key, is there's one specified angle. With respect to this angle, there are two legs, one of which is adjacent to the angle, one of which is opposite the angle. And we have another line that is not a leg at all, it's called the hypotenuse. Hypotenuse, opposite leg, adjacent leg. And these are what the O's and the H's and the A's stand for. The sine, back to your notes, of any angle is equal to the length of the opposite leg over the length of the hypotenuse. That ratio of those two distances, or those lengths. The cosine is defined as the length of the adjacent leg divided by the hypotenuse. The length of the tangent of that specific angle is defined as the ratio of the opposite leg's length to that of the adjacent leg. So when you say SOHCAHTOA, as long as you spell it right, if you botch the spelling, you're hopeless, okay? This means that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. SOHCAHTOA. Okay? So again, if you botch the spelling, you're done, because you're going to get it all messed up. But if you can remember how to spell SOHCAHTOA, then it'll help you out quite a bit. Let's draw this triangle on your paper, if you would, please.
same page.
Yeah, same page, same paper. And we're going to mark a particular angle. Now, what you're going to discover as we go throughout the year, mathematicians use the Greek alphabet a lot, especially in representing angles of triangles, or angles in general. They'll use lowercase Greek letters. So you're actually going to learn the entire Greek alphabet this year, little bits at a time. Not intentionally, that's not the point, but it happens to be something you'll learn. This is the most common angle symbol. It looks like an O with a line through the middle of it. It's actually the Greek letter theta, T-H-E-T-A, and it's the Greek sound. For instance, you might be familiar with the word theos, referring to God. That's actually spelled theta epsilon omicron sigma, theos, okay? But the is not two letters like it is in American or English. It's one symbol, and it's the Greek letter theta. This is the most common symbol used by mathematicians to denote some specific angle, or some angle in general. So we've got this angle theta here. Opposite this theta angle is a line of 8 inches, centimeters, feet. Does it matter? No. Because if you have those units here, you're going to have those units below it, right? And the units are always going to cancel in a ratio. So it doesn't matter if this is 8 inches, because this would be some number of inches as well, and inches would simply cancel. So because I'm lazy, we're just going to say that leg is 8 units, the hypotenuse is 17 units, and this leg here 15 units. We're going to draw this on your paper. We want to find what is the sine of theta. Now notice we abbreviate sin, because we're too lazy to write the E. The cosine of theta, but we're too lazy to write cosine, we just write cos. That's just the first 3 letters. And we're also too lazy to write tangent. We'll simply write tan. So notice we use just the first 3 letters of each of the words. Sin, cos, tan is how it's spelled, but it means sine of theta, the cosine of theta, the tangent of theta. Now Chris is looking at his calculator very closely. He's looking at the second row at the top, and he's like, sin, cos, tan? I always wondered about sin, cos, tan.
I always did, actually.
I knew you did. Everyone does.
I knew that was.
And then Ethan's like, I never even noticed that before. Anyway,
What's a
I always click on it and see if it doesn't.
Anyway, well, it does do something. I'll teach you how to use it here in just a little, well, not this lesson, but later. But this allows us then to find the sine, cosine, and tangent of this specific angle, theta. We're simply going to remember SOHCAHTOA. Sine is opposite over hypotenuse. Well, with respect to theta, what is the opposite leg class? 8. Over the hypotenuse, which has a length of 17. So for this specific angle theta, the sine of the angle is 8 to 17. The cosine, well, SOHCAHTOA. Cosine's what over what, Quentin? adjacent leg over hypotenuse, or I just say adjacent over hypotenuse like he did. What is the adjacent leg's length? 15. And the hypotenuse, of course, is still 17. So the cosine of the angle is 15 over 17. Tangent, TOA. Well, tangent's going to be what over what, Jamie?
Opposite leg over adjacent leg.
All right, so for this angle theta, what's the length of the opposite leg?
Would it be 15?
For this angle theta, the opposite leg.
Okay,
8. And then the adjacent leg, the one that is part of the angle, 15. There we go. Now some people are like, wait, isn't the 17 also adjacent? It's not a leg, it's the hypotenuse, right? So we have two legs, adjacent leg and opposite leg. The hypotenuse is not a leg, hence H kind of stands on its own. But for this particular angle theta, there's our trig ratios, the sine, cosine, and tangent. Draw another triangle if you would. And we'll make our right angle C. We'll make the other two angles A and B. Let's suppose that side AC has a length of 5. Let's suppose side AB has a length of 13. And side BC has a length of 12. If vertices are labeled, there's no reason to use theta or any other Greek letter for that matter. We could simply name the angles A, B, and C. C is the right angle. You don't find trig ratios of the right angle. You find trig ratios of acute angles. Because again, that's what makes the similarity. All right triangles have a right angle. But to get similar triangles, you'd have to have matching acute angles. So let's suppose we wanted to find the sine of angle A, the cosine of angle A, and the tangent of angle A. I like to mark the angle directly on the triangle. It just helps me to focus on the correct thing. And then I say to myself, SOHCAHTOA. It's a pep talk reminding me that trigonometry is easy. And then I think through, and I think sine, class, is opposite over hypotenuse. Again, what is sine? Opposite over hypotenuse. So Chris, for angle A, what's the opposite? What's the hypotenuse?
12 over 13.
12 over 13, good. Then I think ka, like I'm going to pak to ka. For those who are in New England. So cosine, ka. Cosine's whatever what class? Adjacent over hypotenuse. Again, adjacent over hypotenuse. For angle A, what's the adjacent, Ethan?
5.
5 over the hypotenuse. 13. So 5 to 13 is my ratio for the cosine of angle A. And then tangent, I think, TOA. Tangent is what over what? Opposite over adjacent. So for this, Jamie, opposite?
12.
Over adjacent, 5. And there's the sine, cosine, and tangent of angle A. You say, what about angle B? Angle B feels left out. Okay, let's take care of angle B. Let's find the sine of angle B, the cosine of angle B, and the tangent of angle B. What is the sine of angle B, Ethan?
So opposite over hypotenuse. So 5 over 13.
Perfect, 5 to 13. Cosine, ka, Quentin.
12 over 13.
12 adjacent to 13 hypotenuse. TOA, tangent, Chris. 5 to 12. And there we get our sine, cosine, tangent of angles A and B. Questions on that? Now, we do step it up just a little bit here because we don't want to be insultingly easy about this.
Yeah.
So let's combine what we were doing earlier with what we're doing just now. On your paper, go ahead and draw a triangle. And let's label the vertex angle as theta this time. Let's label the hypotenuse as 15. Let's label the base leg as 9. And let's find the sine of theta, the cosine of theta, and the tangent of theta. By the way, notice I don't say angle theta. Theta is assumed to be an angle. The lowercase Greek letter is assumed an angle, whereas A is technically a point. So if you mean angle A, we specify angle A. Do you see the difference? Okay. Well, to find the sine of theta, sine's whatever what class?
Opposite.
Yes, so toa, opposite over hypotenuse. So for theta, what's the opposite? What's the hypotenuse, Chris?
opposite is 9, and the hypotenuse is 15.
All right, so we make a ratio of
15.
9 to 15. We've said before in algebra, anytime you have a ratio, we always reduce the lowest terms. In fact, even in geometry last year, always reduce ratios. The same thing's true here. So rather than leave 9 to 15, we'll reduce it to get 3 to 5. Make sense? All right, cosine. Ka. Jamie?
It's an adjacent leg over hypotenuse.
All right, so our adjacent, wait a second. Did I forget to label something? No, we just have to find it.
Yeah.
How do we find the missing adjacent leg, class? It's not a special triangle to my knowledge, so we're going to go Pythagorean theorem. Find it at your seats. What is that missing leg?
Right there.
Yeah, that's what it's pointing. Like, what is it?
12.
12. There we
I
go.
was like, what?
I was pointing at you because I wanted the answer. All right, 12. How many got 12 for the missing leg? All right, so now, Jamie, we are ready to go ahead and find the cosine. Ka.
So it'll be 12 over 15.
12 to 15. But we won't leave it that way.
We'll reduce it to 4/5.
Good, 4/5 or 4 to 5 since it's a ratio. And then tangent, toa, Ethan.
That is,
Toa.
oh.
So tangent's whatever what? Oa. Toa.
No, that's the opposite over adjacent.
There we go, opposite over adjacent. So the opposite is?
9 over
The
12.
adjacent 12. 9 over 12. So we get 9 to 12, which we can reduce down to get
3 to 4.
3 to 4. Alright, so sometimes you may even have to find a missing leg first and then find your trigonometric ratios. Questions on that? Let me give you a couple of these for you to do on your own. I'll teach you a couple new Greek letters. I'll leave the SOHCAHTOA up there. Not that you couldn't easily write it at the top of your own paper, but you know, whatever. For the sake of those watching on YouTube who haven't turned it off as soon as I said SOHCAHTOA. Yeah, you know. All right, so let's suppose we have a base leg of 35 and a vertical leg of 12. We're going to use this time, it's kind of like theta, except instead of a cross line that stays inside, it's actually like a cross out all the way through. This is the Greek letter phi. It's spelled P-H-I, phi, and it's actually their sound. So if you were talking about, I don't know, football, which I don't know that the Greeks had football, but if they did, or philosophy, the Greeks liked philosophy, that sound is actually the phi. So anyway, find the sine of phi, the cosine of phi, and the tangent of phi. By the way, why do mathematicians like these? Because they don't have to draw the angle symbol every time. I am that lazy. So find the hypotenuse, then find the sine, cosine, tangent of phi. I've got one more I'll put up on the board for you while you're working that one. Don't do the second one yet. I'm sorry. Don't do the second one yet. There's some things on the calculator I want to show you with that one. So just do the first one. I don't know why my triangle is like tilted sideways there. Just do father OCD people, like that thermostat on the far end of the hall. You see that thing?
Oh, yeah.
Yeah, it troubles my soul. All right, what is the length of the hypotenuse, first of all? Because we need that right off the bat. Class? 37. All right, what did you get for the sine of phi then, Chris?
12 over 37.
Good, 12 to 37. What about the cosine of phi? Quentin?
35 over 37.
35 to 37. And Jamie, what did you get for the tangent of phi?
12 to 35.
12 to 35 is correct. So we get those same answers there. Now, a lot of times, like these worked out rationally, they worked out to a ratio of 2 integers. It doesn't always work that way. Sometimes we get weird numbers. And so what we'll sometimes do is we'll round off these ratios to 3 decimal places. Write that in your notes. If it doesn't work out evenly, we'll use 3 decimal places. Now, if we wanted to, we could do that right now. We could, on the calculator, divide 12 divided by 37, and we would get 0.324. Find for me the cosine of phi, if you would.
.945.
Well, but then what comes after the 5 is a 9, right? So that's actually going to bump it up to
6.
But you know, mathematicians are lazy, right? And mathematicians, you all have the point 945, 945, 946 on your calculator? Okay, mathematicians are lazy, right? And we don't want to have to do the rounding in our head, because then even somebody who's smart like Jamie screws up and doesn't round right. Your calculator can round for you. Did I show you how to do this last year in geometry? It's called the fix. If you look above the decimal key, you see it says the word fix. Hit the second button. Doing this with me, Chris. Hit fix, and then tap the number 3. And you'll see it will round all of your 3 decimal places you want, which is perfect. Because when we're working with trig ratios, we want 3 decimal places. There's my 3 decimal places. So let's now, while the fix is on, let's go ahead and do the tangent. We don't have to worry about the rounding. It'll do it for us. We get 0.343. Now again, is it a problem to do your own rounding? No. But hey, why do it when you don't have to?
Yeah.
Be lazy. Questions on this?
How do you do it again? The fixed button, I know that.
Second function, fix, and then tap 3. And it'll give you 3 decimal places. If you tapped 8, it would give you 8 decimal places. But we want 3. So second, fix, 3. And around everything on your calculator to 3 decimal places until you turn it off. Once you turn it off, the fix goes away. Not that it's hard to put it back. All right, so let's take a look at this next one here. The first thing, of course, we've got to do before, by the way, this is the Greek letter alpha. It's equivalent to our A, so it makes that A sound. It actually kind of even looks a little bit like an A if you think about it. Like just imagine a straight stick here instead of little curly cues at the bend, and you can kind of see an A in it. Anyway, we want to find sine, cosine, tangent, alpha, but we first of all, of course, have to find that missing leg, was what I was hoping to hear you say. We first have to find the missing leg. All right, how do we find the missing leg? Pythagorean theorem. So 32.7 square the hypotenuse. Subtract the square of the leg. Take the square root. And what do we get for missing leg?
24.6.
Yeah, it comes out to 24.63, blah, 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 right? Just keeps on going for a while. Oh, that's a pain, isn't it? Let me show you another thing your calculator can do. Chris, doing this with us. Put that on the calculator. If you have not yet, I didn't see you moving. You've got to stay with me on this.
I already have 24.6.9, I did it earlier. So
Okay.
I started working on it earlier.
All right, well, you want it on the calculator right now, though,
Okay.
because of what we're about to do. You don't want to keep up with that number, because you can't even say it's 24.638 because it's not. That's a rounded value. And when you round and then round again, it's just going to mess things up. So here's what we need to do. We need to put this value in the memory of our calculator. Your calculator has 3 memories built in that you can store. So find the button that says STO. It's right here on the left panel. That's your store button. And you can either store it in 1, store it in 2, or store it in 3. So hit store 1. You should see a little M1 pop up in the corner. That tells you that memory 1 has not 24.638 in it. It has the exact value to millions of digits stored in its brain. It can't display the millions of digits, but they're all stored in its brain. Okay? You don't have to worry about storing it in your brain. What I like to do is I like to put M1 here, especially if I'm going to use lots of memories, just so I remember this isn't something I type in, it's in the calculator's brain. Okay? We'll work problems later in the year where you'll use all 3 memories at once. So you got to remember which number is in which memory. Just a habit for now. Don't really need it because we know it's the only memory value. When we go to find the sine of alpha, we know that sine is what over what, class? Thank you, Quentin. Class, what is sine?
Opposite over hypotenuse.
Opposite over hypotenuse. So we're going to take this value that's still on my screen, that's the opposite, and we're going to divide it by, since making a fraction, we can't really make a fraction here, can we? because they're not integers. So we're going to divide it by 32.7. And it'll give me a decimal to 3 decimal places already rounded off. Class, we get 0.753. Now we don't need this value for the cosine because cosine is what over what, class? Adjacent over hypotenuse. So we can take our 21.5 and divide it by 32.7. And with adjacent over hypotenuse, what do we get for the cosine of alpha?
0.657.
Good, 0.657. Now technically we would say approximately this, right? Not equal to that, but approximately that. Now we need the tangent. Well, remember, the calculator's brain has that opposite. Tangent's what over what, class? Opposite over adjacent. So to recall something, you know when you remember you try to recall it? That's your RCL button. So if you hit RCL1, it's going to recall whatever's in memory 1. Now again, it only displays 24.638, but it's actually to millions of digits stored in the brain. So we're going to take that opposite, recall 1, divided by adjacent, 21.5. And what is the tangent of alpha? 1.146. Approximately 1.146. Questions on how to store and recall values?
Mine isn't going to 3 decimal points. I don't know if I accidentally cleared it. I turned it off on accident.
Yep, probably did. Yeah, because it doesn't say fix at the top. Where's your memory value?
It probably didn't clear when I...
No, memories will stay like literally. You turn it off and leave it off for 6 months. Turn your calculator back on, that value's still in the memory. I think when you change the battery, it loses memory. But as long as there's a battery in there that's functional, it'll save that memory as long as until the battery dies. So memories do not go away unless you clear it. So we're done with the problem, right? I don't care about that number ever again in my life. Why do I keep it in the memory? You don't. How do you clear it? If you try to store a 0 in the memory, it'll clear it out. So hit the 0 button or the clear button on your calculator so that your calculator shows a 0 or perhaps 0.000. Try to store it in memory 1. Hit store 1 and you'll notice the memory goes away. The calculator will not store a 0. So if you store a 0, it clears the memory out. Does that make sense? All right, so to store something, store 1, store 2, or store 3. To recall it, recall 1, recall 2, recall 3. To clear it, try to store a 0, and it'll make the memory go away. Yes?
I figured it out. So I was clicking second function 2 instead of second function dot because I thought 2 was fixing.
Oh, no. So the second function is up above everything, not below. Okay?
Yeah.
All right, we figured that out. That's good. Page 6. Page 6 in your textbook now. Let's dabble with our special triangles again, though, and let's combine this idea of sine, cosine, tangent with special triangles. On your paper, go ahead and draw a 30, 60, 90. Go ahead and label the lengths. Of course, we know the 30-degree angle is this one here. So when we find the sine, now this time we don't just mark angle whatever. I actually know the exact measure of the angle. So I'm going to say the sine of 30 degrees. The cosine of 30 degrees. I actually know how big this thing is. The tangent of 30 degrees. And to find the sine of 30, of course, sine is what over what, class? Thank you, Quentin. Class, what is sine? Opposite over hypotenuse. Well, what's the opposite of 30? X, what's the hypotenuse?
2x.
So, but x over 2x, well, wait a second. Remember we said we always reduce. The x's will cancel, leaving me with what? 1/2. Remember, this x is technically a 1x, isn't it? For the cosine of 30, cosine's whatever what? Class? Adjacent over hypotenuse. So for the 30, what's the adjacent? X times the square root of 3 over the hypotenuse, which is 2x. Once again, we can cancel those x's to get the square root of 3 over 2. And then the tangent of 30. Tangent's what over what? Class? Opposite over adjacent. All right, opposite is? Adjacent is? X times the square root of 3. And so the x's cancel, giving me,
1 over 3.
uh-oh, Think back to your algebra
Okay.
days. You are not allowed to have a radical denominator.
Times square root by
So we're
square root of 3.
top and bottom by square root of 3 to get square root of 3 over 3, the square root of 9, which is 3. And that's the sine of 30, the cosine of 30, the tangent of 30. On your calculator now, type in 30 and hit the sine button, the sin button. Notice it says 0.5, that's 1/2. Cosine of 30, type in 30, hit the cosine button. 0.866, well, that's the decimal equivalent. If you were to take the square root of 3 and then divide that by 2, you'd get 0.866. If we were to take the tangent of 30 tan, 0.577. Well, that's what would happen if you took the square root of 3 and divided it by 3. You'd get 0.577. Make sense? We will tend to use exact values, though. We'll tend to use these ratios as opposed to those decimals, because the decimals are awkward to work with. But I want to point out something. The x's keep canceling. Wouldn't it be nice if the x's didn't exist? Well, let's just knock them off here. Instead of here, knock them off here. Let's call this 2, square root of 3, and 1. And these are the new numbers I want you to think for your 30, 60, 90. Don't think in terms of x and 2x and x squared of 3 necessarily. Think 1, 2, and square root of 3. Make sense? Let's do this for 60. Let's find the sine of 60 degrees, the cosine of 60 degrees, and the tangent of 60
Will it
degrees.
just be double everything we just did?
No, it will not be. We're going to see this in just a second.
Is that what you were hoping someone would say that?
No, but you're not the first person to say it. I don't get it every year, but sometimes students say, wait, wouldn't it be double? No. So for the sine of 60, we're looking at this angle here now. Sine is whatever what class?
Opposite over
Hypotenuse.
I was kind of glad that. Let's try this again. Looking at the chalkboard, so katoa. What is sine class?
Opposite over hypotenuse.
That was still really lousy. Let's try to do it in unison here. Ready? What is sine class?
Opposite over hypotenuse.
All right. And so for 60, opposite over hypotenuse is going to be what class?
Square root of 3 over 2.
Square root of 3 over 2. Isn't it easy without the x's in the way?
Oh, yeah.
Not that you couldn't mentally knock out the x's, right? You could probably do that in your head, I suppose, but it's nice to be able to knock them out this way. Cosines, what over what? Class?
Adjacent over hypotenuse.
Good. And what do we get for adjacent over hypotenuse?
1 over 2.
1 over 2, 1/2. 1 to 2. Tangent is what over what, class?
Opposite over adjacent.
And what do we get for tangent of 60?
1.732.
Square root of 3 over 1.
Square root of 3 over
I
1.
pressed.
Or we could just leave the square root of 3. You don't, it's like you have to put it over 1.
He knows what I did.
You did it on the calculator instead of just looking at the values here. All right, questions on this? We could do the same thing with a 45, 45, 90.
Oh,
There we go again.
But for the 45, 45, 90, of course, the sides aren't, x, 2x, and x squared of 3. The sides are
no. 1.
x, x, x squared of 2. But if we knock out the x's, we could think of them as
1 square root of 2.
1 square root of 2, which is just square root of 2, right? So now let's find the sine, cosine, tangent of 45 degrees.
Can I do a little calculator?
No. Because we're also reviewing special triangles as we do it this way. Now, for the 45, you could look at either one of them. Do we want to look at the top or the bottom?
Doesn't matter.
Doesn't, so pick one. Top. All right, Jamie says top. She spoke first. She's also the only girl, so she gets to choose. All right. That's how it goes in life.
Danny.
All right. Yeah, because when you get married, you'll be one guy and one girl, and the girl always gets to pick. It's just how it goes. All right, so 45 degrees. Finding the sine. What is sine? Class?
Opposite over hypotenuse.
And so what is opposite over hypotenuse?
1
1
over
over
2.
Or, yeah.
Which is not acceptable.
1 over square root of 2. When we multiply top and bottom by square root of 2, do it in your head.
Not square root of 2 over 1.
Square root of 2 over square root of 4, but square root of 4 is 2. So square root of 2 over 2. All right, cosine is 1 over what class?
Adjacent over hypotenuse.
And what do we get?
1 over half square root of 2.
1 over square root of 2.
Same thing.
So again, square root of 2 over 2. So the sine and the cosine are the same.
Who would have
Huh. Interesting. All right, tangents, what over what class?
Opposite over adjacent.
Okay, we fell back into our old habits. What's tangent class?
Opposite over adjacent.
Good. So what's the tangent of 45?
1.
1 over 1, which
One.
is 1.
We should have known though, I mean, it's 1 and 1, so we should have known they were gonna be equal.
Interesting. There's some observations we'll make on this a little bit later on. For now, I want to change gears here just a little bit. If you have your graph paper, go ahead and get it out. And remember, on a graph grid, such as we talked about in your algebra days, which seems like a long time ago, back in, really long ago for poor Jamie, but on the graph grid, of course, we have, let me drag this over here, we have a couple of crisscrossing lines. These lines are called
Cartesian quadrant.
the lines themselves are called axes. Okay, so you may want to write that term down. Axes. We have two of them. We have the x-axis, it says right there on the poster, and we have the y-axis. Let me zoom in just a little bit for our YouTube audience. So we have axes, the x-axis and the y-axis. Okay, remember this? All an axis is, though, is a number line. It starts at 0 and goes to infinity, or 0, negative infinity. Vertically 0, up to infinity, 0, down to negative infinity, right? We call the 0 point of each axis the origin. The origin, right? That term down. So we have the origin, that's where the axes intersect. It's been a long time, I told you. The origin, that's why we're reviewing. And as these axes cross each other at the origin, they make 4 sections to the graph.
Quadrants.
We call those quadrants, okay? So go ahead and write the term down just by way of review. We call them quadrants. Now, every single point that you could possibly imagine on the graph will have a specific x value and a specific y value. I have the point P marked here. It has a specific x value of whatever this is, and has a specific y value of whatever this is. I'd be really impressed if you remember this. What do we call the x value of a point?
What does it start with?
Starts with an A.
An A? I think I know what the y is.
Abscissa.
Yeah.
The abscissa.
No.
I'm going to write that term down. Again, it's been a long time. The abscissa is the x value of the point. You remember the y value by any chance? Now that I've said
What does
abscissa.
it start with?
And starts with an O.
Oh, is it the origin?
Ordinate.
Ordinate.
Ordinate. I knew it was around there.
Ordinate. Okay, so the ordinate is the y value. And when you put them together, with the abscissa and the ordinate together, you get the point's location, or the point's coordinates. Good, Quentin. It's the easiest. Coordinates. None of y'all said it. It's the point's coordinates. All right, so some terms that we need to know here. This is referred to, by the way, as the Cartesian plane. Hence, these are Cartesian quadrants that we have up here. The Cartesian plane, named after René Descartes, also called the coordinate plane. These sections, these quadrants, notice quadrant 1, remember here, then quadrant 2, then quadrant 3, then quadrant 4. So it forms the letter C as you go around, if that helps you remember Cartesian or even coordinate, either word. Starts with C, so remember the order there. But basically, remember your positive x's and your positive y's. If both x and y both have cis and ordinate or positive, the point would fall in quadrant 1. If you have a negative x value but a positive y value, it'll fall here in quadrant 2. Quadrant 3, of course, has negative x and negative y. Quadrant 4 has a positive x but a negative y. So remembering all this, all coming back to you now. It's just been a little while. All right. One of the things we want to look at is this idea of from one point to another on one of the number lines. So let's zoom back in now on just the number line itself. How far apart are 2 points? For instance, if on a number line I have the point 2 and I have the point 8, how far apart are those 2 points? 6 units. What's the easy mathematical way to get that? Subtract, right? So to find distance, you simply would subtract one value minus the other value, if you will. Let's just say it's on the x-axis. We just subtract the points. However, what if you looked at this as point 2, or this is point 2 and this is point 1, 2 minus 8, they're negative 6 apart? Does distance really have a negative aspect to it? No. So we say that distance can be found by the absolute value of the points subtracted. What if I was interested in the distance between this point 8 and the point negative 3? How far apart are those points? 11. Because when you subtract the negative, it's adding the positive. Or you just think there's 8 units here, 3 there, that's a total of 11 units, right? So to find distance between points, we simply would subtract them away from each other. Turn your books, if you would, to page 8. Page 8. By the way, page 7, you see that some of those graphing terminology there, if you wanted to study those, or you study them from your notes.
Would you recommend it?
You have your notes. Number one, it says draw a number line. So go and get your graph paper out. I'm only going to need a number line, so I'm just going to make a little bit of something here. On the graph paper that I told you yesterday to make sure you brought with you today.
Oh, you're
I
using
mean, actually, I
freebie?
should-
Oh, I forgot you just used it.
I just used it last class, my bad.
And used it earlier this
I
hour.
used it Spanish, my bad.
All right, go ahead and draw a number line. Put your arrows on the ends, put a 0 sort of in the middle. And then maybe label every 3 increments is what we like to do. Every 3. We want a line that looks like this, Chris.
Oh.
Apparently. All right, and on exercise number 1, really easy exercise, they just want us to plot these points. So they want us to plot the point -2. Well, on your number line, find the point -2 and plot it. Did you put it right here? 1 unit over from -3.
Roughly.
I hope you did.
Roughly.
Then the next point it wanted was the point -square root of 3. Get your calculator out. Take the square root of 3 and then tack a negative onto your answer. Now you can't take the square root of -3. So you have to square root of 3 and then tap the negative button at the bottom. What is negative square root of 3?
-1.732050808.
Right, -1.732 blah blah blah. Well, if this is -2, where is -1.7-ish?
Right behind it.
Little bit to the right of it, correct? A little less negative. Notice -1.7 is pretty close to -2, right? The next point they want us to plot is -square root of 3 over 2. So if this is -square root of 3, then if I just divide it by 2, I'll get -square root of 3 over 2. So divide that answer on the calculator by 2 to get -0.866 if you still have that fix on. So where would that be?
Below 1.
Here's the -1. We want to go just a little bit further to the right of -1. And maybe zooming in here just a little bit would help the YouTube audience here. So we've got -2, just a little left of that -1.732 or square root of 3. And then square root of 3 over 2 is a little bit here beyond the -1 or closer to 0 than -1. Then they want us to plot 1. Don't blow this one. Did you all get the 1 in the correct place?
Roughly.
Yeah.
All right,
Well-
square root of 2. Calculator. It's the square root of 2.
1.4142.
All right, so picture where halfway between would be. Not quite halfway between. Because that'd be 1.5. We want 1.414, so almost 1.5. Make sense? And then they want square root of 5. Calculator. What's the square root of 5?
2.236.
Okay, so here's 1, here's 2. We want to go a little bit past the 2 to get the square root of 5. Questions on how to find radical values on a number line. Very quickly, stay with me for just a second. We'll do these orally. What's the distance between 2 and 4?
2.
2. What's the distance between -2 and 3?
5.
5, right? We've -5, but absolute value, so 5. What's the distance between -4 and 2? 6. What's the distance between m and n?
And -n.
The absolute value of m minus n. What's the distance between m and -n?
Absolute value.
7 letters.
The absolute value of m
And
plus n minus -n, right? And anyway, we'll work on that more tomorrow. Homework for the evening is to do page 6, numbers 1 through 3, page 8, number 3, page 9, number 7. These each need to be on separate graph grids. So make 2 Cartesian planes, 1 for number 3, 1 for number 7. All right. So I would recommend just do the whole homework assignment on a sheet of graph paper. Might be the easiest thing to do. Or in a graph paper notebook would be convenient. All right, we'll take a look at that tomorrow. Have a wonderful rest of your day, and you are dismissed.